Hello there everybody. So today I'm going to be talking about the topic of to what extent can an epidemic be mathematically modelled. And the reason I want to talk about this is that coronavirus has had very peculiar growth, and I want to see how well an epidemic can be modelled. And as there are lots of mathematicians out there who try to model epidemics, and let's see how accurate these models are. So I think this could be a really interesting topic to talk about. So to start off with, I'm going to be talking about epidemiology. So epidemiology is a branch of medicine that looks at the spread of diseases, their distribution, and how to control them. Now there's lots of maths within epidemiology, such as calculating differential equations, and using different models to predict the outcome of an epidemic, and calculating the probability of recovery for a patient. So these are all interesting things that we need to take into account when we're looking at epidemics. There are also statistical analyses and other methods that you can look at to help model this growth. When I say model, I mean like plotting a graph, sort of, that shows how the number of infected people changes with respect to time. So, for example, a graph showing plotting the number of people infected against time since the birth of the outbreak of the disease. So the main model we're going to be looking at is the SIR model. This is the foundation of epidemiology, and let's talk about the SIR model then. So the SIR model, or SIR model, stands for the susceptible, infected, and recovered. The susceptible is modelled as S of t, where t represents time passed since the outbreak. There's also I of t and R of t. So what susceptible means, pretty much, is that how the susceptible people is people who haven't yet got the virus. These are ordinary people who haven't been infected yet. And at the beginning of the outbreak, this is the entire population. And for this model, we're going to let the entire population equal to n. So the susceptible is anyone who can get the disease, which is everyone, apart from people who are immune, but the SIR model doesn't take this into account. Then the infected is the people who have been infected by the disease. This is self-explanatory, I don't need to really talk about this. So you go from being susceptible to being infected, and then go from infected to being recovered. So recovered, this is people who have had the disease, and they've either recovered, they've been cured, or they've passed away. So if you add the susceptible to the infected and the recovered, you should get the total population. And you can do some basic small mathematical sums. For example, if you divide the total number of the susceptible divided by the population, you can see what fraction of the population is susceptible. Same for infected. Divide the infected by the total population, you can see what fraction of the population is infected. Okay. So if we can break down the SIR model into three differential equations. A differential equation is pretty much an equation that models something, that tells it to you with respect to something with respect to something. So for this, we're going to be looking at the rate of change of the susceptible with respect to time. So the first equation is ds by dt equals minus beta si. Beta is the rate of change. Beta is the probability of becoming infected. This needs to be times by the number of susceptible and the number infected, because you're imagining that all the susceptible and infected people are interacting with one another, and then the probability, if you times that by the probability, that tells you how many people are infected on a given day. So it's going back to that, it's the total number of people infected times the total number of people who can be infected times the probability, and that will tell you the rate of change of the number of susceptible. And the reason this is a negative number is because you're always losing out on susceptible people. The susceptible number doesn't increase, it can only decrease, so it's a negative rate of change. The second equation we'll be looking at is di by dt equals beta si minus gamma I. Beta si is the same as before, as we are gaining the number lost from the susceptible category. The people lost from the susceptible category go into the infected, so there's an increase, so there's a positive rate of change. But then we're also minusing gamma I. I is the number of infected, so you times the number infected by the chance of recovery, which is gamma. So the chance of recovery times the number infected tells you how many people will recover each day. So the rate of change of infected is the people becoming infected minus people becoming recovered, pretty much. And then let's move on to the third equation, which is dr by dt equals gamma I, where gamma I is the same as it was in the previous equation. So this is, in the previous equation we had minus gamma I, as people are going from the infected category to recovered, so they're recovering from the virus. So for the recovered category, this is again a number. So gamma times I is the number of people recovered from the infected category each day. So yeah, that's quite interesting. So we can break down these equations even further to try and calculate how severe the virus is, because if di by dt is less than 0, then we know that the epidemic will not be a threat. It will quickly dissipate, and it doesn't really matter, as we can see that more people are recovering than getting the illness, hence there is a negative rate of change of the number infected. If the value is greater than 0, so di by dt is greater than 0, then we know that the epidemic is growing, and it's growing over time. So this would cause the epidemic to grow rapidly, so this is not a good thing. So for the equation, we're going to be using di by dt equals beta si minus gamma I, which is the same as before. And we're going to be working at t equals 0, because what epidemiologists do, they look at the rate of change in the number infected when at the beginning of an infection, so when there is no time, when time equals 0, and they're seeing if the epidemic will grow and becoming something big like the coronavirus, or if it will just quickly disappear and there'll be no low transmission rate. So we're going to be swapping out the S for S0, which represents the initial susceptible, and I into I0, and we're testing whether di by dt is less than 0. So if you write out beta S0 I0 minus gamma I0 is less than 0, then we know that I0 must be 1, because there's at the beginning initial people infected will always be 1. You cannot have 0 infected, otherwise there will be no virus, and it usually stems from 1 or 2 people. So we're going to say I0 equals 1, so we can cancel out the I0s, so we get beta S0 minus gamma is less than 0, and then if we add gamma to both sides, we get beta S0 is less than gamma, and then divide both sides by gamma. We have beta S0 over gamma less than 1. So this epidemiologist, they use this equation and they rearrange it to equal R0 equals beta S0 over gamma, and R0 is the rate of infection. So if the rate of infection is greater than 0, then we know that the epidemic will be a problem. But if it's less than 0, we know it will not be a problem. So we end up with the total equation of R0 equals beta S0 over gamma. So from here we can see that R0 is directly proportional to S0 and beta. So by decreasing any of these, we'll have a decrease in the infection rate. So since beta is the probability of becoming infected, if we reduce this, it will reduce R0 as they're directly proportional. So we can apply this to modern model problems. So we can see that by social distancing and quarantining, we can decrease beta, and this will decrease R0, which is what we want. We're trying to decrease the infection rate. And then you can also decrease S0, which is the initial susceptible people, by introducing a vaccine. A vaccine will prevent someone from having the epidemic, so the number of susceptible people will be lower. So if you have a vaccine, you inject it into someone, someone goes straight from the S category to the R category, so they can no longer get the virus, which is what we want. And then as it's directly proportional to R0, decreasing S0 will decrease R0, which is good. Okay.